Thank you. So thanks for giving me the opportunity to give a talk. It's nice to be in Bonn. So this talk is about ends of non-positively curved manifolds, and it's joint work with Tam Nguyen Phan. So let me start by telling you what I mean by non-positively curved manifolds. So I mean Mn is going to be a complete Riemannian manifold. And it's also going to have finite volume and curvature between -1 and 0, possibly including 0. So non-positively curved and bounded. And so here is the schematic picture that you should have in mind when you're thinking of such a manifold. It's something like this. Again, maybe it's not compact, but it has finite volume. So this is the manifold M. Sorry. I'll try not to do that again. And then you can look at its universal cover. Because the manifold is non-positively curved, the universal cover is contractible. So it's in fact, it's homomorphic to a disk. And then when I say the end, I mean this region over here. And I'll be more precise later. Somehow, in nice cases, this is going to look like some closed manifold cross array. But it's the complement of a compact set. That's what you should think of when I say the end for now. And so one can look at the end here, and one can look at what it lifts up to in the universal cover, and it's some sort of, I'll just draw something for now. And so then the question is, green is probably not a good color. Okay, the question is, what's the topology of this? That's, for now, the way question. What's the topology of either the end or what it lifts to? So to give you an idea of what to expect, I want to give some examples. So the first example is a non-compact hyperbolic surface. So a hyperbolic surface. So you can think of the surface, so M2 is what you get when you take a torus, you remove a point and you stretch it out. You can give that a hyperbolic metric. So this is a punctured torus. The picture for this is, well, it's the same picture as here, but instead of schematic, now it's an actual picture. Well, still not an actual picture because I can't draw something of constant curvature -1. But it looks like this. And it's not compact. But the way in which it's non-compact is somehow, it's very mildly non-compact. So this end looks like S1 cross array, 0 infinity. And then you can look at its universal cover. And the universal cover is the hyperbolic plane, which I'll draw in the disk model, maybe H2. So the hyperbolic space. And this shaded region lifts to something that in this picture looks like a bunch of disks touching the boundary. And by a bunch, I really mean infinitely many, but I'll only draw finitely many of them. Okay. So somehow this is a very simple picture that we have for a hyperbolic surface. Now the next thing, which is slightly more interesting, is what happens when you take a product of two such hyperbolic surfaces. So this is example 2. So product of surfaces. So in this case, the manifold M is now a 4 manifold, and it's homomorphic to a punctured torus cross a punctured torus. And a good way to draw this, to draw the geodesic picture of this, is as follows. Let me try to do that. So these are my two surfaces that I'm taking the product of. And then you go to infinity in different ways. So the resulting end is more complicated. And it's, in some sense, in a well-defined sense, made up of several pieces. And so it turns out that this manifold is still the interior of a compact manifold with boundary. There's still this end, and it still looks like boundary across an interval from 0 to infinity. But this boundary now has more structure. In fact, it's made up of two pieces. There's one piece that looks like this, and one piece that looks like this. And so let me maybe write that here. So in this case, the boundary looks like a surface with an end chopped off cross S1 glued to S1 cross a surface with its end chopped off. So this is a three-dimensional graph manifold. And this part is right here, and this part is right here, and they're glued along a torus, namely an S1 cross S1. So that's the structure of this manifold. And if you look at its universal cover, right, its universal cover is a product of two hyperbolic planes. So let me draw it up here. So M tilde, it's homeomorphic to just a four-dimensional disk. And up here, you have these kinds of pieces, and they lift to something. I will maybe draw it like this. They lift to to disjoint things, disjoint disks or disjoint spaces. And there are also these kinds of pieces, and they also lift to disjoint spaces. And there are actually infinitely many of them, but I'll just draw this many. And maybe to draw a more suggestive picture, I should draw this disk not as two-dimensional, but as at least three-dimensional. So really, you should think of something like this. OK, so that's what the universal cover looks like. And the important point to take away is that because these things overlap up here, you can actually have some topology. So the structure is more interesting than what you had over here. OK. So this example was somehow, well, both of these examples were a special case of a large class of non-positively curved manifolds, which are called locally symmetric spaces. So the third example is locally symmetric manifolds. And these are things that, well, one way to say it is that they have the form G mod K mod gamma. And I won't tell you carefully what G, K, and gamma are, because that's not what this talk is about. But you should think of something maybe like SL3R mod SO3 mod SL3Z. And instead of SL3Z, to get a manifold, you need to take a finite index subgroup of the right sort. OK. So there are spaces like this, which are called locally symmetric spaces. There is a more complicated picture than the one for products of surfaces, but there is an analogous picture. So, and I'm going to draw it. And I'm not going to use these colors again, because it didn't work out that well. So the picture will look schematically something like this. This is my manifold M of some dimension n. There's some topology over here. And then there is the end. And the end is now made up of several, it's made up of several pieces or tiles that overlap in some fashion. And again, this end looks like a boundary cross array. And when you look at its universal cover, when you look at M tilde, sorry, this is homeomorphic to a disk. And these things, again, lift to some sort of spaces that overlap in some pattern. And one knows a lot about exactly what this pattern looks like for these locally symmetric spaces. In fact, one knows that this pattern, this is always homotopy equivalent to a wedge of spheres, to an infinite wedge of spheres. So a wedge from 1 to infinity of spheres of a certain dimension. The dimension is called Q minus 1. So this Q is what's called the Q rank. It's defined in terms of what this G is and what this gamma is. Again, I don't want to tell you what it is, but I want to tell you something about it. Well, maybe the thing that I will say that I think is suggestive is that for these locally symmetric spaces, this Q is always less than or equal to the dimension of the locally symmetric space over 2. And so one can think of some examples. So for these hyperbolic surfaces, which are also locally symmetric spaces, this Q was 1, and the dimension of the manifold was 2. So in fact, sometimes you have equality. So this Q is actually equal to the dimension of M over 2 for a product for a product of a bunch of these hyperbolic surfaces. But often it's less. So it's homotopy equivalent to a wedge of spheres. I mean, somehow up there, it's homotopy equivalent to a graph, and it ends up being a wedge of spheres. So it's not, that's a wedge of zero spheres. I guess I should say it that way. It's a wedge of zero spheres. The zero sphere is 2 points. So, yeah. Okay. So this is somehow a very interesting structure. But it comes out of really the algebra of what these locally symmetric spaces look like. But if you think of them as non-positively curved manifolds, it's nice to try to figure out whether one can get it out of the non-positively curved geometry, or one can get some aspect of this, some part of this out of the non-positively curved geometry. Okay. And so that's what I want to talk about next. So let me start by talking a little bit more about the balls, the disks that I drew over there. Okay. So the disks that I drew over there, you can describe in the following way. So this is H2. This is, again, hyperbolic plane in the disk model, the Poincaré disk model. And you can do the following thing. So take some geodesic ray. So start at some point and go to infinity. Take some geodesic ray in the hyperbolic plane. And then start drawing disks, start drawing balls that are centered at points on this geodesic ray and whose boundary passes through the initial point. So this is 1, this is 2, 3, and you keep drawing them, and they get bigger and bigger, and they squeak. And so you get a union of all of these things. And the union of all of these things, that's what's called a horoball. So this is called a horoball. And its boundary is called a horosphere. Horosphere. Or sometimes a horocycle. Okay. And so this is in the disk model. It's also instructive to draw the same picture, essentially the same picture in the upper half plane model of the hyperbolic space. So this is half plane. And right, this is less symmetric, but sometimes you see more. So if you pick the geodesic ray that goes straight to infinity and do the same construction, start drawing these bigger and bigger disks. Then what you will end up getting in the end is you'll get just another upper half plane shifted up. So that's going to be your horoball. And the horosphere, its boundary, is going to be this. And it's just homeomorphic to R1. Okay. So that's the picture. Right, I drew this picture for a hyperbolic plane, but actually this description makes sense for any non-positively curved, for any simply connected non-positively curved manifold. In fact, it doesn't even have to be a manifold. So somehow this works very frequently. And I'm going to talk more about it in a bit. Let's see how much time I have. Okay. And now I want to sort of make a short digression. And the short digression is a story that I read in the notices a few months ago, almost a year ago. And this is a story by Dennis Sullivan about William Thurston from 1972. And it has to do with horospheres. So that's why I have an excuse to read it to you. Okay. So this is the Institute for Advanced Study in 1972. One day, walking towards lunch at IAS, I asked Bill what a horocycle was. He said, "You stay here." And he started walking away into the Institute meadow. After some distance, he turned, stood still, saying, "You are on the circumference of a circle with me as center." Then he turned, walked much further away, turned back and said something which I couldn't hear because of the distance. After shouting back and forth to the amusement of the members, we realized he was saying the same thing. "You are on the circumference of a circle with me as center." Then he walked even further away, just a small figure in the distance, and certainly out of hearing, whereupon he turned and started shouting, presumably the same thing again. We got the idea what a horocycle was. Okay, so that's the story, and the moral is that in 1972, Sullivan didn't know what a horocycle was, and Thurston explained it to him by illustrating the definition physically. Okay. So that's, and so in this picture, I should have labeled this point S, and this would be like T1, T2, and then T3, etc. Anyway, okay. So these are what these balls are, and now now in the upper half plane model, you see that there's a special kind of symmetry, special kind of isometry that looks like just like a translation, just shifting this way. And this translation preserves this horosphere up here. But there's an interesting feature about this translation that you can see if you think about what does the metric on this hyperbolic plane looks like. It looks something like dx squared plus dy squared over y squared. And because of that, this translation, so up here it moves a point by a certain amount. If I move further along this geodesic, it moves that point by a smaller amount in this metric, and the amount is smaller because the denominator is getting larger. So this translation, you can go up, and it's moving points by less and less. So this is somehow a special kind of isometry, and which is called a parabolic isometry. So now I want to spend a few minutes telling you about what isometries in non-positively curved spaces can look like. So let me erase this. And I'm not going to use this device because I haven't been in Germany long enough to use it efficiently. So instead, I will use this more primitive eraser. Yeah, I see why that's probably better, but still. Okay. So isometries in the hyperbolic, not in the hyperbolic, in non-positively curved spaces. So the situation that we have is, well, so the situation that we had was we have the universal cover of the manifold, and the fundamental group is acting by isometries on it. And let's look at one, so pick some element in this fundamental group. Then one studies, so it moves points in some fashion. Like it takes some point x here and moves it to gamma x. Right. It moves points in some fashion. And one way to study these isometries is to look at what's called the displacement function. So this is d gamma. This is a function on the universal cover, which assigns to each point the distance it moves that point. So it's a map from the universal cover to the non-negative real numbers, which sends a point to the distance between x and gamma x. Okay. So this is called the displacement function. And for these elements in the fundamental group, maybe for non-trivial elements in the fundamental group, there are two kinds of isometries that one can distinguish in terms of this displacement function. The first kind are isometries for which this displacement function attains its infimum value. So let me write it this way. Infimum of d gamma over points in the universal cover is attained. And what should you think of? Well, again, one can think of the hyperbolic plane and look at something which is translation along a geodesic in this hyperbolic plane. So here is a geodesic, and well, on this geodesic, your isometry is translating along. And for anything else, for any other point, well, you connect this point to the closest point in the geodesic, then you move along the geodesic, and then you go back. And if you, so this defines an isometry. And moreover, these points are moved by the least amount, these other points are moved more. So in this case, the infimum displacement happens exactly on this geodesic. And this is a general feature. So these, in this case, this isometry preserves a geodesic. Right. So I said I'm looking at elements of the fundamental group that are non-trivial. So more generally, there is a third kind of isometry, which are things at fixed points, but I don't want to talk about them in this particular instance. Yeah. So this infimum is attained, and it's not 0 because otherwise you wouldn't be in the fundamental group. Okay. And right. So this is what the picture looks like upstairs. When you take the quotient, that means that you have a small, well, you have a geodesic loop of some length. If this was this length with L, then there's going to be a geodesic loop down here of length L. And I guess maybe it's not embedded but immersed, but that's okay. So length L. Okay. And this is, again, this is a general feature. Instead of hyperbolic space, I could have written just some other here non-positively curved manifold and its universal cover. And it's just for the following reason. So if you take some point that's moved by the least amount, how do you find a geodesic that's preserved? Well, you take this point and you translate it. So this is gamma x. You translate it so if it's moved by the minimum amount, this distance is exactly L. And then what you want to happen is that if you translate it again, you get your geodesic. But this might fail. The way it might fail is there might be some angle over here. Oops. That's an even more primitive eraser. There might be some angle over here. So it might look like this instead. But it turns out this can't happen. And the way you see that this can't happen is you take the midpoint, let's call it y. It gets translated to the midpoint over here, which is gamma y. If there was an angle, then this distance is going to be strictly smaller than L, which cannot happen. Smaller. So actually, you don't have this picture. You have that you're really translating along a geodesic. And there could be more than one. I mean, there's nothing says that there's just one. There could be a bunch of sort of parallel geodesics along which you're translating. So these are, oh, I haven't said what these are called. These are called hyperbolic isometries. Okay. And the second kind are isometries where this infimum is not attained. So this infimum inf d gamma is not reached, not attained. And these are called parabolic isometries. And so this translation right here in the upper half plane was an example of a parabolic isometry. That's somehow the prototypical example of what a parabolic isometry is. And in this case, what it did was it preserved this horosphere. It actually preserved this horosphere right here. And that happens more generally as well. So if you have a parabolic isometry, it again preserves some horosphere. And I want to draw a picture which sort of gives you an idea of why that is, how you find horospheres that are in fact preserved by these things. So you have this infimum. Let me pick numbers that approach it. So t1 greater or equal to t2 greater or equal to etc. And these approach this infimum displacement. And now again, let me draw a picture of the universal cover. So sort of, I'm drawing maybe this part of it. So this is a manifold, the universal cover. This is its boundary at infinity. These are just endpoints of geodesic rays. Okay. And now look at the sets where the displacements of gamma are getting smaller and smaller. So here's what they end up looking like. So there's some set. The displacement of gamma is less than or equal to t1. This is called a sublevel set of this function. And it turns out to be a convex set because of non-positive curvature. And then there's another where displacement of gamma is less than or equal to t2. And then there's another displacement of gamma is less than or equal to t3. And you keep going like this. I mean, there are more. And now, how do you find points at infinity? How do you find these preserved horospheres? Well, here's one way you can do it that turns out to work. You pick a point, and then you find the closest point in this convex set to this point. So you find something that meets this at a right angle, and then you extend it to hit some point at infinity. And then you do the same thing here. Find the closest point and extend to hit some point at infinity. And closest point. And I'll draw one more. And so in this way, you get a bunch of points at infinity. I mean, you get infinitely many, right? As these Ti approach the infimum. And then you take any limit point of these, So somewhere in here, let's call it psi. This is some limit point. There may be more than one, but there is at least one. So this limit point is, if you take a horosphere, right? So these horospheres were defined. You need a geodesic, and then you can draw these bigger and bigger balls. So if you do that, over here, you have this geodesic going this way. You draw these bigger and bigger balls. Oops. Then this horosphere is going to be preserved by the element gamma. So this is not obvious, but it is true. And maybe the reason why you might think that it might be true is because these sublevel sets, right? So this function, the displacement function d gamma, well, it's invariant under gamma. So d gamma of x is equal to d gamma of gamma x. This is not hard to see. So these sets are also invariant under gamma. The initial point isn't, but it turns out that nonetheless, this construction is invariant enough so that the resulting horospheres are preserved. And again, so there might be more than one, but it turns out that this angle here, this angle is less than or equal to pi over 2. And the reason this angle is less than or equal to pi over 2 is because, well, so because this angle is greater or equal to pi over 2. And what that ends up meaning at the end of the day is that there might be many different limit points, but they're all within pi over 2 of each other. So somehow there are many choices, but they're all not too far away in a precise sense. Anyway, so this is what a parabolic isometry gives us. It gives us points at infinity where these horospheres are preserved. Okay. So maybe that's enough about isometries for now. So let me tell you one more thing about non-positively curved manifolds, namely what's called the thick-thin decomposition. And, well, so recall that the injectivity radius, so recall what the injectivity radius is. The injectivity radius is a function on the manifold M such that the injectivity radius at a point is the radius of the largest embedded ball. So it's the maximum radius r, such that if you look at the exponential map at the point x, the ball of radius r is embedded, so is embedded into the manifold. So I'll draw a picture in a moment, but before doing that, let me write down one more thing, two more things. So the epsilon thick part, or the thick part, m greater or equal to epsilon, this is the set of points in the manifold where this injectivity radius is at least epsilon. So right, greater at x is greater or equal to epsilon. And the thin part, m less than or equal to epsilon, is the set of points where this injectivity radius is less than or equal to epsilon. So now here's the picture. So there's my manifold. Again, I'll draw the same kind of picture. Over here, somewhere over here, if I draw an embedded ball of radius epsilon, if I draw a ball of radius epsilon, it's embedded at this point. So here, the injectivity radius is greater than epsilon. On the other hand, if I'm over here and I draw a ball, then it will not be embedded. It will overlap itself when you try to embed it. It will fail. And here the injectivity radius is less than epsilon. Okay. So over here in the cusp, in what I drew as a cusp, the injectivity radius is less than epsilon. So somehow this manifold decomposes. There is some region which is this m less than or equal to epsilon. I should say this is called epsilon thick, the epsilon thick part. And this is called the epsilon thin part. Okay. And now, and this picture suggests that the thick part is compact. And this, it turns out to be true, and it's just because, so your manifold, so if your manifold has finite volume, then this thick part is compact. Because if it wasn't compact, then it would be unbounded, and that means you would be able to pack an infinite number of epsilon balls into your manifold, and you would have infinite volume. So this is compact if the volume of your manifold, volume of M, is less than infinity. Okay. And then the question arises, sort of, what can one say about the topology of this thin part? So what can one say about the topology of this? So the first thing that I want to say about it is the following. So this is a theorem of Gromov and Schroeder. It's somehow a generalization of a theorem of Gromov and a specialization of a later theorem of Schroeder. So that's why I'll put both names. And the setup is this. So you have an n manifold, and it has finite volume, and it has a curvature between -1 and 0. And it has this additional condition, which I'll explain later, that there are no arbitrarily small closed geodesic loops, closed geodesics. And if one has a manifold of this sort, then for small enough epsilon, this thin part, m less than or equal to epsilon, again looks like a closed manifold cross 0 infinity. So it's homeomorphic to a or diffeomorphic to a closed, well, homeomorphic to a closed manifold cross 0 infinity. And so again, if you try to draw a heuristic picture of what one should be thinking of is, well, so you have your manifold M. When epsilon is kind of big, when epsilon is not too small, there can be some features that this thin part is picking up, like this region over here. It's not too thin, but it's still thin. And so maybe then the thin part is like that. But as you keep shrinking epsilon, these features go away, and you're just left with something that is encoding the topology of the end. And so that's what you should at least think of when you think of this theorem. Yeah, the boundary can have many components. I just don't want to, I mean, so you could have this. Yeah, this is the one time in this lecture when I will actually draw more than one component. Homeomorphic. Is that? Well, so it depends on which paper you read. So I don't want to be too precise about it. I mean, the slogan is that the injectivity radius function has no critical points outside a compact set. And now you say, what does it mean to say critical point? Because if you think of this function, it's not a smooth function. So you have to either smooth it out a little bit, or you have to generalize your definition of critical points. And Schroeder does this sort of more carefully than Gromov does, not surprisingly. But so homeomorphic is true. I don't know about more generally. So you should think of that this injectivity radius function has no critical points outside compact set. Again, this is a slogan, more or less. Okay. All right. And so now I want to make some comments about this condition that there are no arbitrarily small closed geodesic loops. So this is frequently true. Yes. I'm not saying it's unique, if that's what you're asking. Oh, well, so I have a Riemannian metric. I mean, what this is? Emle. Well, so I have a Riemannian structure. The Riemannian structure tells me what m less than or equal to epsilon is. So this is just a set. Well, so it ends up being a manifold. It has corners, so it's not smoothly embedded, but it's a manifold. I mean, you should, yeah, right, yeah. Well, I mean, you have to show that the topology doesn't change, and I don't want to dwell too much on this. You can ask me a bit more about it later, and I will be happy to talk to you about it. Okay. All right. So maybe one last comment. Somehow these small geodesic loops, they're things that cause some topological changes, but then you have to, I mean, there are other things that might cause topological changes. And anyway, but let me now make a comment about this. So this is frequently true. It's true for, so it turns out to be true for locally symmetric spaces. And it's also true for manifolds of negative curvature, -1 less than k less than 0, where the important thing is that this is a strict less than. But it's not always true. And in fact, there are examples. Yeah, so it's not always true. And there are examples when you have what's this? So there are three-dimensional examples, actually. There are three-dimensional manifolds where you have arbitrarily small geodesic loops, and the manifolds are of infinite type. So the fundamental group is infinitely generated, so nothing like that is true for them. So somehow this is, again, it's an important condition. And this is an interesting example. I might, again, I can tell you about it later, but I don't want to spend time on it right now. Okay. But then, so this leads to the question, what can you say about the topology of this boundary? And again, there might be more than one. I'm not saying that it's necessarily a unique. So what can one say about topology of this boundary? Yes. Yes. Mm-hmm. Well, I'm not saying it's true for every epsilon. I'm saying that there are epsilon for small epsilon. Right. That's what is in Gromo's paper. He says that. Delta? What's delta? Oh, this. No. So for sufficiently small epsilon, you have that this delta is a reparameterization of epsilon. I mean, reparameterization of epsilon. For sufficiently small epsilon, the injectivity radius function doesn't have any critical points. That's yes, right. Yes, okay. That's right. That is right. Well, I'm going to talk about, well, you can't, I'm going to talk about a weak version of that. So, well, I mean, I think in general to really describe delta carefully is hard to say. I mean, one can say something about it, and I kind of want to say, give some information about what you can say about it. And then, again, then I might be able to answer more specific versions of that question. So here is the theorem, or here's a theorem. Oops. So again, let me draw that picture again. I'll draw it with one cusp because it's easier. So this is my manifold, and I picked an epsilon that was small enough so that this end looks like boundary. So this m less than or equal to epsilon looks like is homeomorphic to boundary cross array. And then I look at the universal cover of this manifold. And I look at what's lying over this shaded region, and again, it might have some topology, so I'll draw it like this. Right, so this is like a dn. And then, so you want to study what the topology of the shaded region can be. So you look at some cycle inside of this, or something mapped into this. So let me draw. I'll use this. Let me draw something that I can kind of draw. So there is some kind of topology in here. So this is, more formally, this is going to be a map from a finite polyhedron into this region lying over the epsilon thin part. So let me write this as the cover of the epsilon thin part. Right, and this is a finite polyhedron. Then the theorem is that this phi can be homotoped in this region lying over the thin part to a map phi hat, which factors through something low dimensional, where low will be, well, I'll say in a moment what low means. That factors through n over 2, floor of n over 2 minus 1 dimensional polyhedron. Right. So if you're looking at this picture, what this is saying is, in some sense, that this thing that I drew as a surface might collapse. You might be able to homotope it to collapse it to something that looks like a graph instead of a surface. Right. Well, essentially, there is this half-dimensional bound n over 2 minus 1. Okay, so let me. So I want to say a few words about this theorem, but before that, let me mention some applications. Okay, good. Some corollaries of this. This is the same conditions as in Gromov's theorem. So so n manifold, finite volume, non-positive bounded, non-positive curvature, and no arbitrarily small closed geodesic loops. No, it doesn't have to be locally symmetric. No. So the right, the red thing is just giving examples when you have no arbitrarily small geodesic loops. Oh, so P is a finite polyhedron. So what I want to do is I want to look at cycles in this region, but I want to say something slightly more general, which you'll see why. So instead of just cycles, I also look at maps in that might be more complicated than cycle. Yeah, from a but it has to be finite. Yeah. Right. That's the statement. Right. And so the corollaries of this. So there are a couple. Well, I'll divide them into two pieces. There are a couple. The first one is that this tells you something about the homology of this. It tells you that the homology in dimension greater or equal to the floor of n over 2, that this vanishes. Because you represent the homology class by a map from a polyhedron, and if it factors to something of lower dimension, then that means it dies. Okay, and this should be, you should think of this as something analogous to what was on this board a long time ago, or maybe it was on that, no, it was on that board a long time ago. There is a trace of it left, q less than or equal to dimension of m over 2. So this is somehow one part of what we saw for locally symmetric spaces. And the second corollary is that if the dimension of m was less than or equal to 5, then each component of this boundary, there might be more than one component, but each component of this boundary is aspherical. So then boundary is aspherical And this is just because, well, so you check whether it's aspherical by looking at maps from higher dimensional spheres. If n is at least 5, if n is at most 5, so 5, the floor of 5 over 2 minus 1 is 1. So then you actually get a graph, so factor through a graph. And therefore, you can collapse these higher dimensional spheres. I mean, you can contract these higher dimensional spheres. Okay. And this is somehow why I insisted on maps from polyhedron and not just sub. Well, also technically it's easier to deal with these. Okay. And then there are a few more things that, curiously enough, are just about the fundamental group. So you can get something about the fundamental group from that statement. Right? So the fundamental group of M acts up here. Let me call it gamma, just so that the statement is shorter. Then you can get that the group cohomology in dimensions, this was less than or equal to the floor of n over 2. This is in dimension less than the ceiling of n over 2. The group cohomology with group ring coefficients is equal to 0. And again, I can tell you more about this later. It's a not too difficult consequence of this. So, I mean, if you apply the right kind of Poincare duality, etc., you can get to this. But somehow this is nice because it's something about the group. It's not something about the end of your manifold. And finally, the fourth thing, which is again a consequence of, essentially, you can get it as a consequence of this, is that if instead of a manifold, you look at an aspherical complex with this fundamental group, then the dimension of that aspherical complex is at least n over 2. So the geometric dimension of gamma is at least, well, the ceiling of n over 2. And again, one can get this without too much work from here. But I don't want to talk about it right now. I want to say a few more words about where this theorem comes from. Okay, good. Well, so here's so how can you try to do this? How can you try to collapse this to a lower dimensional thing? Well, here's the first thing that one might try to do, and I'll say, sort of not to keep you in suspense, the first thing doesn't work, but it's supposed to illustrate something. So take a geodesic ray here. You can take a geodesic ray that goes to infinity, and then lift it up to a geodesic ray up here. And then try to push the entire cycle just to this point. So if you try to do that, well, this picture is getting crowded, I'm sorry. Yeah, maybe. Well, I'll still do this, but okay, well, so you think of trying to push all of these along geodesics to this point at infinity. The reason why this might be something worthwhile to do is because when you push to this point at infinity, your cycle doesn't stretch. It either shrinks or stays the same size. And this is a productive process because, so if it had some given diameter, if you go into the end far enough so that you've moved at least that diameter, then you can contract your whole cycle inside of a ball. Then you would be able to do that. So that would be a positive thing. Now, the negative thing is that in the process of doing that, you're passing through here, right? So this is lying over the thick part. So that's not good because, I mean, you want to be able to, you're asking about the topology of just the thin part. Okay. So that doesn't work. And the thing that you try to do instead is you try to push different parts of the cycle to different points at infinity. And they need to be somehow intelligently chosen points at infinity, so that when you do that, you don't leave the thin part. That's the first part. And second, once you've done it for individual points, you need to have a way of connecting. So you don't just push points, but you also push edges. You also push triangles, etc. And okay. And so let me draw a few more pictures to illustrate some of this. Yeah. Yes. Yes. So the thing is, I'm starting out here, right? So really, what it's saying is, this geodesic ray that I drew, if I'm taking this point, it's something that's asymptotic to the same ray, and it might be, it might first push in until it pushes back out. So if you think about what this is down here, it means that there's something that maybe takes something over here and then does this, and eventually pushes out. So eventually you're going to be fine, but eventually it's not good enough somehow. And I mean, the reason why you know that this can't work is because for things like a product of surfaces, etc., you had this picture, and there was some topology. I mean, the thing was homotopy equivalent to a wedge of S1s. So you couldn't possibly have contracted this S1. So and it's because of this. Okay. So now, so now let me zoom in into that picture. So zoom in into maybe this region and draw a picture of that. So this is the boundary at infinity, and then this is the part that lies over the thin part. And so here is, and this whole, everything is happening in the universal cover. And there are parts of that cycle. I'm not going to use yellow because it's too much work. But anyway, so there are some points on the cycle, maybe x and y, that are part of that cycle P, and you want to figure out how to push them to infinity. So first, let me make a comment about what is this thing that's lying over the thick part? What can you say about it? Well, if you go back to this picture, if you're on the thin part, what does it mean? It means that this ball is not embedded. So if you thought about that up in the universal cover, what it means is that there are two translates of the ball by an element of the fundamental group that overlap. So there's, I don't know, this was point y. There's y tilde, and then there's gamma y tilde. And this distance is epsilon, this distance is epsilon, so the total distance is less than 2 epsilon. So another way to describe this is the set of all points in the universal cover such that the displacement of some isometry at that point is less than 2 epsilon for some non-trivial, for some non-identity element in pi 1. Okay, and why is this good? Well, it's good because, so look at this point, for instance. Well, so it's saying there's some isometry, maybe call it gamma, that moves it to a point over here, gamma x, so that this distance is less than 2 epsilon. And moreover, this condition that there are no arbitrarily small closed geodesic loops means that this isometry, when epsilon is small enough, this isometry was parabolic. Because if it was hyperbolic, then you would get a geodesic loop of length at most 2 epsilon. And once you're at a scale where there are no such things, you know it's parabolic. Since it's parabolic, you can find points at infinity that are fixed by this. So pick one of them. So there's a point here that's fixed by it, preserved by it. And that means that the translate by gamma of this geodesic is this geodesic. That means that this distance as you go along doesn't get any bigger. So it always stays in this thin part. And for this other point, you can do the same thing. There might be a different isometry here that's small. Maybe it's called rho of gamma. And it's again parabolic. This is less than 2 epsilon. You get some other point at infinity. And again, this distance is again small. So that's why when you're finding points at infinity, in this fashion, you're at least staying in the thin part, which is progress. And now you sort of think, well, how would you connect? So in this cycle that I was drawing, these 2 points are connected by some edge. So how would I push this edge to infinity? Well, so first of all, if these points started out being far apart, then subdivide so that they're actually fairly close together. So let's pretend that they're close together. If they're close together, then this isometry rho and this isometry gamma, they're both small over here. I mean, there might not be small less than 2 epsilon, but they're less than 2 epsilon plus delta. And the fact that they're small means the following. It means that the group generated by these isometries is not hard to understand. And this is what's called the Margulis lemma. And it says that in that case, this group gamma rho it's virtually nilpotent. And this is somehow why it's crucial to have bounded non-positive curvature, because otherwise you don't know something about the structure of these groups generated by small isometries. and this index is also uniformly bounded in a certain way. Okay. And there are some tricks you can do to get from a virtually nilpotent group to a abelian group built out of this. I won't tell you what they are, but so for now we'll pretend that this is actually just an abelian group. Okay. Now, so for this group, I again want to find a point at infinity that's going to be preserved by gamma and rho. And let me tell you somehow how one should try to find that point at infinity. Well, so for this isometry gamma, we found a point at infinity using the displacement function of gamma. For this isometry rho, we find a point at infinity using the analogous displacement function of rho. For this group, you try to find a point at infinity using the sum of the displacement functions, d gamma plus d rho. And why is this a worthwhile thing to do? Well, because if you can draw the following picture. So here is a sublevel set where the displacement function of gamma is less than or equal to some constant a. Here is a sublevel set where the displacement function of rho is less than or equal to some constant b. Then inside of both, you can write down there is a sublevel set of the function d gamma plus d rho, where the displacement is less than or equal to a constant c. And you can figure out what this c should be. It's not hard, but I won't do it right now. And this is a good thing for the following reason. So if you try to do that construction, right, what I need to do? I need to draw the closest point on this displacement, on this sublevel set, the closest point on this sublevel set, and the closest one on this. And when you draw these, you will see that this angle and this angle are less than or equal to pi over 2. This is less than or equal to pi over 2. And the reason is the same reason why the possible choices up there were less than or equal to pi over 2. And the consequence of all of that is that in this picture, if I pick a point at infinity according to this added up displacement function, then these points will be within pi over 2 of each other. I mean, after some work, etc. But they'll be within pi over 2 of each other. And this is good, because if you know some non-positive curved geometry, it's good because points at infinity in what's called the Tits metric, points at infinity that are within pi over 2 can be connected by unique geodesics. So if this point is preserved by gamma, and this point is preserved by gamma because it's preserved by a bigger group, they're within pi over 2. There is a geodesic that connects them like this, and that's also preserved by gamma because it's unique. So there is at least a way to find what you probably should be pushing these edges to. So that's, again, progress. And in the last couple of minutes, let me just say, so I mean, there's some other, so by doing something like this, you end up getting a map, let's call it phi infinity, of the polyhedron into the boundary at infinity. And this map is nice in several senses. First of all, these points that you get, if you project down to the manifold, they end up looking like this. They end up they might wind around for a while, but eventually they diverge. Also, the things connecting them will eventually diverge. So you're pushing further to infinity, and that gives you more space to then collapse your cycle down to something lower dimensional. And the thing that you're collapsing it down ends up looking like the image of this at infinity. So the question that then you have to look at is, what's the dimension of this? How big can the dimension of this be? And the half-dimensional bound somehow comes. This is the last thing I'll say. The half-dimensional bound is essentially the following feature, that this dimension of phi infinity of p is less than floor of n over 2. This comes out of two things. The first of these has to do with, there's some, you have these elements, you have groups. When you have larger simplices, you have larger groups. But if the dimensions, so groups of small rank, if your groups have small rank, that implies that the dimension of the thing at infinity is small. That's maybe not that surprising. If you have two groups that agree up to finite index, then you might imagine that you can send it to the same point at infinity. What's maybe more surprising is that if you have groups of large rank, that also implies that this dimension is small. So, I mean, the groups I'm talking about is you look at groups generated by small isometries at these individual points. Yeah. And maybe one last thing, namely, so here, because you have this larger group, it fixes this point. If you look at this point over here, well, if gamma and rho commute, so gamma rho equals rho gamma, then this function is also invariant under rho. So this function is also invariant under rho. And that means that you might believe that this horosphere is also invariant under rho, and that's true. So in fact, this simplex is invariant not just under this small group, but under this bigger group. So you have this simplex, and you have this group. And then the key is to show that for appropriate simplices, that the homological dimension of this group plus the dimension of the simplex, the topological dimension of the simplex, is less than or equal to n minus 1. And this is somehow a whole different lecture about what kind of simplices you have to use, etc. But I'll stop. So, yes.